Is it readable?
Yeah. Yeah.
Really don't like this. Okay. I have a timer, but if I'm do this. Okay,
I'll tell you.
And this afternoon to celebrate.
Oh, really? Okay, I think let's start up again. The recording part. Okay, so for the second talk of this morning, we have Francesco, and he's going to tell us about, well, Hodge-Shapley value.
Yeah, it's a long title.
A long title. Yes.
Yeah, it's too long.
Go ahead.
Okay, thank you. So, thank you to the organizer for inviting me and for organizing this. As many people say before, I'm very happy to. It's the first time I go speaking in person to a conference since 2020. So I'm very happy also for this to be here. So today I will share with you some of the results we have obtained together with my student, and now is going to discuss the thesis quite soon, Antonio Mastropietro, PhD student. And so this is our joint work. It's a part of his thesis. It's something we have really done together. And so the main theme here is, as the long title say, is try to understand how we can extend the Shapley value, whatever it means, to a coalitional case. And I will explain all the detail in order to obtain some new tool toward solving problem in so-called explainable artificial intelligence. So I have two versions of the talk. This is some questions. So why Shapley? The question we try to understand, to answer today. What is limited? Explainable artificial intelligence is a really a huge topic, very hot now for some reason. And these things is easier to explain by example, but I have also realized the 40-second talk. So if you are in a hurry, I will do this and then we go. So no, here really is what we will do. We solve an equation in terms of Laplacians over a graph, which is the poset graph of the subset of a fixed set. And so most of the things here are about semantics more than calculation, because it's the meaning of the things, not what you calculate really. And solving this equation, we find that the solution is unique. We build an analogous of the Shapley value, again, whatever it is, which is defined over the vertices over this graph, whose vertices are subsets. And so in game theory terminology, coalitions. And we will see that this solution, this is quite unexpected, is unique. Is the unique solution of this problem, is the unique, what is called game map, satisfying a kind of Shapley axiom for a coalitional version of Shapley. Shapley is something that I explain now, okay? And practically, the purpose of this is to find a system to evaluate the contribution of groups of features in machine learning instead of finding information about the single feature, which is what Shapley is doing in machine learning, explainable machine learning. So now let's go more seriously to a very, very quick introduction to the problematic of explainable machine learning, but actually in this case, not explainable AI, but explainable machine learning. So this is the basic scheme of what most of the algorithm in machine learning does. In particular, if you are working in a so-called supervised setting, no? So you have a certain set of data, which theoretically are assumed to be sampled IID from some unknown distribution. IID is fundamental, otherwise many of the bounds that are on error to give an estimation to error that fail, it doesn't work. And in any case, usually you have here some sort of H, this H here, which is so-called set of hypotheses. You can think there are any kind of things we will see after, but practically there are archetype of functions. Okay, so from neural network to linear regression, multilinear regression, half planes, whatever, you have a certain family of function. They might be also quite strange in theoretical machine learning, at least like things like rectangles with edges parallel to the axis. So they are not analytically described, okay? In any case, what you do, you use the so-called empirical risk minimization. So you try to minimize some loss. Some way you have to measure how far you are from the desired result. There might be misclassification, cross entropy, come si dice, mean square error, whatever. It depends what it is. Okay, abstractly is in this way, and then you go back to your data. You have this, I call them the unsolved. You have this test data that you never touch along the path, and you simulate testing the data outside of your experiment. Okay, I don't want to go, tons of details that there are on these things. Okay, just to make so as an example, typically the set of hypotheses typically is made of something determined by parameter and hyperparameter. It depends what they are. No, it depends. As an example, if you take a multi-layer perceptron, it has the number of layers, the number of neuron each layer, which activation function, and these are all hyperparameter defining the archetype of your candidate model. And then you have a way that may be more or less complicated. We have seen before talking about gradients, stochastic gradient, backpropagation, stochastic gradient descent, whatever you use. Somehow you try to find, I don't say the best, I don't say that you really find the minimum in your list, but you are looking for something near to that. You try to minimize your loss somehow. And this turn out at the end, providing you really, usually, in a function. No? So as an example, here you have affine half spaces, which are very simple to describe as function, probably is the simplest beside the constant function. And with this, you can do SVM, You can also do it with kernel and so on. But I mean, the mechanism is this. And as an example, if you have, as I said before, you have MLP, you have all these parameters. What happened? It happened that practically, when you finish your work, you build a function that in certain cases might have something like million of parameters or thousands of variables. In machine learning, people call them features usually, or predictors if they are more on the statistical side. But in any case, you have all this amount of things. So technically, it's not true that this is a black box. I mean, it's something very clear. But even if you write down explicitly the composition of a fine transformation and ReLU, let me say, of a multi-layer perception with, I don't say much, 100 layers, you find the function that you don't know what to do with that. You put your faith because it's too complex. There are too many variables, too many parameters. It's very difficult to understand what. As an example, what is the role in eXplainable? I try is a very large area of research which is devoted to try to understand how to get rid of this mysterious behavior. There are many problems and themes. One of the themes is related to understanding the role of the various features involved. Why this is important? For several reasons. You know that nowadays many of these models are in production and are used to make a decision, as an example, concerning the people's life, related to health issues, as an example, insurance, justice, whatever. And so, besides that, in Europe, we have a law that pretends to ask accountability of the algorithm, which is something that I think is quite unfeasible, because even if you imagine the layman say, the bank didn't give me the loan because the computer said that I'm not compliant. Then you go there, you explain, yes, because here you have we have performed an autoencoder with a variation autoencoder with regularization by Kullback-Leibniz divergence. And the guy say, okay, so what are you talking about? So no, so the point is this, but also there are other issues. But the actionability is one of the problems with machine learning. Is there's 90% is a posteriori. Is describing something on the basis of what it was. It is able, like you remember the famous paper on breast cancer using neural network made by some people in Berkeley. I don't remember the name. They were able to find the trait in the slice the human weren't able to find, and so on. But the point is that, and then, so what? When I know this, what I do with this? I give you a big system that is telling you are mayor of a town, and I tell, okay, the population there is not happy because you measure things, and they say, yeah, but where I have to push to change it? If you talk with company like I do, they are very interested in understanding what they call actionability. How can I sell more cars? How can I make this better? You make an anomaly detection system, but they don't want root cause detection. You say, why you have this? Where I have to go to change? So one of the points is say, I have a, let me say, okay. So there are various ways of doing this. Very popular was, and it is layer-wise retropropagation, LRP, which goes, an example, on network, back in the network, trying to maintain some quantity constant and trying to understand the role of the various neurons in a decision. But it turns out that this has some problem they made some sanity check. They see that even if you change, perturb very dramatically the internal layer of the network, LRP doesn't change. So it seems that there is some problem, probably because practically, if you also see, imagine you have a network making classification. Practically, layer by layer, you're seeing your data in a higher dimensional space. You try somehow to separate them, but the real decision is made by the last two layers. So what's happening inside seems to be nowadays still mysterious. In any case, one of the ways it has been suggested is to try to use game theory. and in particular a certain kind of game theory that I'm going to introduce. They're called a transferable utility game. So the idea in practice is the following. A transferable utility game is, I need my glasses, and so if you, like me, start as an algebraist, you say, okay, it's a vector. So it's a vector. So it's a list of numbers, nothing else. It's the interpretation that is important, okay? From strictly mathematical point of view, this is simply a list of, is a vector whose entries are indexed by the subset of the set. And you ask, you say, you have a game if the vector has the empty set 0 and the empty set entry equal to 0. Practically, the idea is this: you have some something, a good, and you form a coalition to try to obtain this good, and you have an evaluation of the result. This is the concept. It's something that is very old. And I mean, it was at the very beginning of game theory, things made by von Neumann, Morgenstern, and Shapley. So, no, questo è okay, so I give you a couple examples because I do not assume in this environment all the people know this thing, that it's not complicated. This is an example. So it's very simple. You have a man which leave 1 million to his nephew, but they can have the million only if at least 2 of them agree on how to divide the money. So practically, what you have below is the so-called strategic form of the game. So you have that no one is and one singleton, they all give 0 because you have no agreement. You have to imagine that a little group means they agree, okay? And so you have all the other group agree, and so the pay is this. This is really trivial, but the idea is this. This is very famous, is practically the first example in all game theory book, is the globe game. So practically there are 3 guys, one has a left globe and the other 2 have a right globe. And they want to sell the globe, but they need to have a pair. And so if they don't put together, they don't gain anything. And this is the form, okay? I will not go on in this. There are, as you can imagine, there is something enormous on this. There are books, there are thousands of pages. There is a lot of definition, classification. A game is additive, subadditive, monotonic, cohesive. That part I find quite boring, to say, but it makes sense. So the idea is due to Lundberg, in Lee, 2017. And the idea was to try to build a construction to use transferable utility game, thinking about the feature involved in your machine learning model. Think your favorite machine learning model. You take the feature, they are player, they concur in generating the outcome of the model. Pay attention, this is not about training. The model is already trained. This is about the decision taken by the model after you train. You train the model the best you can, and then you put, meat in the mechanism, you get sausage. But you want to understand how it makes the decision. So they introduced the so-called sharp explanation game. The sharp explanation game is a game which assigns to a group of features, a coalition of players, the expected value of the model. You fix, I didn't write it. Okay, I write now the advantage of doing this. Okay, X star is a fixed sample. So I put X star into the model. X star means simply you take a sub list of variables. Okay? You project, if you like. And you evaluate this. And so, okay, we have a game. But we want to give some value to the feature to understand which feature concur more in deciding X or Y, cat or dog or whatever. And here's some notation just to fix. I use, as is usual in this setting, GN to denote the set of game. and on n player, and I call a payoff a vector whose entries are indexed by the number of players, and simply is an allocation of something, of a worth, to the various player. The key point is that, given that I have this game in strategic form, so each coalition has a certain worth, like before with flows or more complicated things. How can I distribute the worth of the grand coalition when they are all together among the player, taking into account the various worth distributed among the various coalitions? So there are a lot. This is really about economic theory. There are a lot of theory about this. So you have egalitarian, you know, it's a cooperative game, and each one head, one share. So you take the number of you take u of n, you divide by n, and each one has the same. Shapley was not of this kind, was a marginalist. So the idea is then to use this Shapley value and the Shap game to try to make this redistribution of the decision. Okay, scusate perché non vedo bene. Allora, okay, so okay, this is maybe I have done something very wrong. What I have done? Wait a second. Yes, this is something just to visualize, because I really don't know the people here how much is involved in this thing, so don't feel offended by it's very naive. So I imagine you have a neural network, and you have a picture of a cat or of a dog and so on. You have trained this network to make segmentation or recognition of something in a picture. And the picture, how it works, usually you have this feed-forward mechanism. This is oversimplistic. These things usually is a long list of convnet. There are convolutions, so it's more complicated, but just to have the abstract idea in mind. And you have activation of the various neurons, blah, 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 and then at a certain point you arrive at the end and it's a cat. So the idea is that I want to find a way to say which of these pixels, so which of these guys, wait to make a sort of ranking, let me say as an example, of this guy participate in making the decision. I think the concept is clear. Okay, this is Shapley in a picture that I like because seems like a old sage or something like this. I don't know. He died, he passed away in 2016. He won the Nobel Prize, and this Shapley thing that everyone calls Shapley value and so on actually was his PhD thesis. So was a smart guy. Anyway, let's see how it works. Shapley value. So this is the definition. Then we see that there is a magic definition because it does exactly what they want. Okay, this is the first definition. Let's try to understand what this writing here means. So given a game U and a feature I, so the Shapley value phi I is defined by this formula, is the average practically over the symmetric group, all possible permutation, of this delta I of S sigma of I. What is delta I? Delta I is what is called the marginal contribution. So I take A and I measure how much the worth of A increase if I add the player I. In the example before, the single player has value 0, then you add another player, the nephew, and the value go to 1. So in that case, it's symmetric group, and these are the preceding coalition, preceding I. So practically the idea is the following. I change the page so we look at this. The idea is the following. Imagine your player entering in a room in random order. You make all possible entries, and then you measure how high contribute when is added is the one that entering at that stage. Okay, so 3 people enter, then I enter, 2 people enter, then I enter, and so on. And you do it in all possible way, and it is easy to see that combinatorially it is becoming this way. Because simply the number there, S, is because you permute the people, keeping you know, the same people, but you permute the order in which they enter. No, you have I, and then the people before, and n s minus I are the people coming after. So you get this. Okay, so just to give a little example here, take this super simple game. There in the column there is the game. Okay, so I have given an attribution to the various coalition, and this is the computation of the Shapley value. You see, you have all possible order in which they enter, and the number under the player, pay attention, is not the value of the game on that player, but on their player plus all player before. So as I try to write down, write up maybe there, here, I can use this, which is better. You see it, the meaning of the first row is there, and all the same. And the Shapley value are the averages for each player or their contribution among all possible permutation of the people entering in the room in any order. Okay, problem with this. First problem is here. This formula is nasty. It's gigantic. N is big enough. If you work with genetic data, you have 10,000 players. So write down that. Compute that is practically impossible. There are approximated version of this. One is called Shapley, and if I don't remember well, there's kernel Shap, another, and some of them, I have to say, they make overly simplistic assumption, like that the variable are independent, which is not. I mean, no way. Okay, you can, if you are brave enough, you can try to apply ICA and try to make it independent, but then you lose any interpretation. And besides that, if you have 10,000 variables, playing PCA or ICA is not so simple. You have a lot of problem with the eigenvalues, as an example. Okay, so in any case, there are some approximated version, but the key point for us was this, because you can frankly, you can say, okay, this is a formula, but why you use this formula, this combinatorial thing? And the explanation on this, there are these which are called fairness axioms and came from economic theory. They say something, no? They say efficiency. What is efficiency? The worth distributed among the features, I say, instead of games or of players, must be, the sum of these must be equal to the total sum. You do not waste anything. This is the first. The second point, if you do nothing, if you are a null player, then CI of you must be 0. Okay, you are not obliged to know null player, I realize now. And so null player means practically that U of A union with I is equal of union of A for all A in N minus I, okay? So practically, if you are there or not, nothing changes. Like those guys that stay in a corner in a party, you know? Nobody and even perceive their presence. Symmetry is the obvious thing. For all coalition that makes sense, if you add I or J, nothing changes. U of I union I, A union I is equal to U of A union J. And A must be suitable. I and J are not there. Okay, linearity, in the principle was not linearity. They asked almost for some, but then it was clear that you can a little bit cheat and use this is okay. So the point is that given this, that makes really sense somehow. The Shapley value is the unique value for a given a Q game that satisfies all the action. There's no other. There is another sibling of this, which is called Banzaf value, as a little bit different and satisfy a little bit different action. Having this kind of result lead us to the idea, shall we formulate this again for coalition instead of for a single feature? And what are their axioms for coalition? Because it must be not exactly the same, no? It must be a little bit different thing. And but besides this, how we can do with coalition? And here iterate Hodge decomposition. So first step. This is not an idea of us. This is 2000. Let me check. I don't remember. I go back. Stern, 2017. Yes. Okay. So this is clearly something that you perfectly know. So the idea is this: build a graph whose vertices are the coalition, and connect those coalitions. Tettenor and Stern were more interested in the traditional Shapley value. So they connect only those ones that are increased by 1. So the Hasse-Quiver of the poset of the subsets, nothing else. Huh? Okay, segments, only segments. So our idea was very simple: take their work, redo it again, allowing any meaningful connections. So take A and B, A contained in B, and try to mimic what they have done, changing what has to be changed. And we succeed, but one of the proofs of this example is 10 pages, because there's a lot of computation. Maybe in the future we will be able to better understand in depth the reason why this works, and to clean the proof. But for now, it's brute force. Okay, so I spare you. I can give you the proof, but anyway, you know these things. Simply, we put ourselves in a very simple setting. We take the graph that I just described. This is a general graph, and we use very plain things with R, usual canonical basis, you know, and inner products such that this is orthonormal, so Euclidean, everything very simple. So that if you go with basis and matrices, D and D star are simply D and the transposed. Then what happened? This is what we started with, the basic thing. You have this kind of what we may call an hypercube, no? Because this is simply the hypercube in 0, 1 to the n. Okay, you take only the edges. Okay, so so here you have the differential I told you before, the classical differential, no? Taking, you know, I mean, is basic thing, and taking the difference of the value, but you can partialize this. You can decide, I compute other map similar to the differential, simply taking only increment by I. So this is depicted by coloring the edges. I hope that the color are readable, because maybe one is too similar, often one is color blinded because I put all this red. In any case, okay. So this is the Tettenor work, and the point is that working with this and using the Hodge decomposition, which actually in this case, to be really fair, is more than topology we should call linear algebra, because this is simply the fact that if you multiply A times A transposes times A, you have this decomposition. There's nothing else. There's a really linear algebra over a characteristic zero field. Very, very super basic things, okay? In any case, in this case, again, what is important is the interpretation. And practically, it is clear that using this decomposition and taking the orthogonal projection on the image of the differential, you can express the di of u as a differential of something. And you call this differential ui, this something ui. It turns out that if you restrict the two games, so you fix the u of empty set equal to 0, D is injective. It's very simple to solve. I mean, the reason is clear. H0, that is 0 is 1, is connected. So the kernel is one dimensional, but the point is the kernel is exactly those vectors that are constant on the vertices. So it's done. Okay. So with this in mind, we have this. And this is the candidate in the sense that sorry, there is a unique solution for the reason that I have said. And it turns out, this is the point, that the Shapley value is exactly this UI is nth component. You make some computation, and the reason is the following. You write down the action, you saw that most of them are satisfied practically by the entire vector UI, right? Which is a game, actually. And but it turns out that, as an example, the symmetry is satisfied by the last component, un, And so since the theorem of Shapley, this is unique. There's no, so this is Shapley. So when we saw this, it was very interesting because, you know, you see those formula here with all this mess, no? This on game, finding that this actually is, you can find it by using the differential on cochain. For me was very, very interesting and stimulating. So the idea, after some thought about how to extend this, we decided to go on. Sono andato troppo avanti? No. Yes. And this is what I was telling. The proof practical is this. So you show that, they show that you have all these properties. Practically, these games, the UI game that we can call high differential game, are a decomposition of the original game. And this decomposition has the particular fact that the last component, the one computed, it's a game, computed on the entire collation, is producing exactly the Shapley value. And yes.
Is there, if you think about this as trying to kind of organize the utilities of the different coalition actions, is there a way of interpreting what comes out as kind of obstructions to utility or some, right, like a gradient flow part or a cycle part, or is there a way of interpreting?
I'm not completely sure I understood what you mean. You are talking about the machine learning model that would come out.
What come out? Is there a way of thinking about these?
Yes, this is the things we were. Maybe I've gone through this too quick. Let's see. Where is gone? No, fuck. Don't say. Okay, it's here. This is the way. This is the way they propose, but there are other you can imagine. So what comes out from the machine learning model when applied to a point is considered, you take the expected value, etc., and you assign to all coalition of features a value, a worth, let me say, and so that you have a game. Then you apply this sharp thing that I told you, and you find a way of giving. So this is not, I mean, esoteric. These things on Hodge and so on is not super popular. It comes out on a paper in some economic journal on economy. The sharp algorithm is even is in scikit-learn. And if you, even in Orange, you take Orange data mined, there is interpretability, there is the graph, typical graph of the sharp with the silhouette of the feature and their value. So is implemented per se. This is one thing we want to do. We want to do it for coalition, the same thing. So the key point is this, for us at least, there are various coalitional proposed for coalitional Shapley value, but my purpose now is not to make a comparison because it's not the purpose of this conference. We have done in this work, there is some comparison with the other approach to construct some coalitional value. There are several, but practical, our idea was very simple. So take the graph we have seen before, but instead of taking only edges like cube, we take it full, okay, like this. Take it full, take all comparable set, and try to understand what is the contribution of a coalition S with respect to a coalition T. You know, the formula can be nasty because you can also consider intersection, but the main proof go on, you consider disjoint subset, and you add one to the other. Consider coalition like fellows, okay? And using this, you can practically mimic the game that we have seen before. So you start, you have only to define what is this LS, US, and so on. Aspetta che però ho saltato una cosa. Yes, it's here. Okay, the S practically is the same as the I. So you move in direction S, adding S, where is possible to do that. And so you try to put all these things together and see what happens. So let me say, doing this in this way costs nothing. You do, then you don't know what to do. In the sense, you find something that you don't know what it is. The key point was not described in this, but this is a simple calculation, because what we have said before remain for the same reason. The Laplacian is injective over games and so on. Nothing changed for connectivity reason. And so the key point is that we define the coalitional Shapley in the same way. So we take US of n, where now US is computed with the system that I told you before. So mutatis mutandis is the same thing. But the key point that making very painful calculation, we were able to discover that it has a very simple form. In this case, it becomes this formula. This is the value that we have found using all this differential and so on. And you say, okay, so what? So first thing, there are axioms, and that's the only one satisfying this. There's nothing else. So the fact that there's a very simple expression is good. You know, when you make some complicated computation at the end, you find a very simple expression. Somehow you guess it. You say, maybe I'm trying to do something. You know, in Italy we say we pay more for the sauce than for the fish. You know, and but at the end, this simplicity makes this more feasible for computation. Even though clearly here there is an exponential issue, because you have to consider all subsets, and you can consider to use only part of the subset. As an example, in a persistent fashion, you can filter on the size of the coalition, or you can threshold and consider partial Shapley values somehow, okay? Because this is computed directly from the value of the game in a very simple way. And so this is what we have found. What I can add to this, any question on this? Is everything clear? Please.
Go back to
This one?
one more.
This one?
Yeah. So here, I think I'm not understanding something. Because if you take S to be a single one, this looks like I can calculate your Shapley values without going through the combinatorial sum.
Exactly.
And so, but this is entirely equivalent. If I take S to be a single, then I don't have to do that. I don't have to take the sum over all permutations.
No, but this is not. Yeah, but this is not the Shapley usual. It's do not coincide with the Shapley.
They don't coincide.
No, because I can tell you this. I didn't include in the talk because I was not. It was not clear to me how much time I needed to do this to explain. But we have made comparisons. As an example, what you produce with this is a game. What you produce with Shapley is a string of n number, which is only what is called an imputation. Okay, you're sending number to the player. I produce number for all subsets, for all coalitions. So actually, this is a game key. Okay. First, second, if you look for the value for the key I, let me say, consider this key, not the Shapley key. You use key and you look for value for features. Clearly, this is not the Shapley value, because otherwise the sum will not. The sum of all this on all coalitions will sum up to the grand coalition worth, and the Shapley value only with n sum up to the coalition worth. So you cannot get the same value. This is another thing is this. That this thing that you see here is a Shapley value, but of something else.
Right, and I don't know what that is.
Is the Shapley value of what is called quotient game by S. So you take your game and you consider a quotient game done this way. It has only two players, S and minus S. Okay.
But this seems strictly more useful, because we go back to the cat example. Single pixels don't tell me that it's a cat. I have to look at collections of features, right? And so this feels like it's strictly more useful in Shapley game. Is that true?
No, I don't know. No, this is simply an interpretation. So this is the Shapley value for S, which is one of the two players. In the quotient game, was player are S and N minus S. The quotient game is like a modular. You regroup and then you consider subset, and the value is obtained by computing the game on the union of the things. Okay. In general, you can take a quotient game by listing a subset, and even better if it is a partition, like this case, and you obtain a new game. And if you compute the Shapley value, the original Shapley value for this quotient game here, you get exactly this. Not exactly. Yes, you get this.
So if you don't fully enumerate, right, start with some subset, is it possible to start with that subset, get a value, then maybe do some type of Monte Carlo onto another part of the subset, recompute? And is that coherent, or do you need, right, the entire?
No, you don't need the entire thing, because the computation is quite local, as you see. You need only to know the value of the game on the coalition and on the complementary coalition. Once you know these two, you can compute this. If you want to compute the entire key, you need to compute everything.
But so you could actually think about sampling.
Yeah, you can. It's a good idea.
Yeah.
Sampling, you make a random partition and then you compute on that and make an estimation. Yeah, also because you have some natural constraint. As an example, you can measure the difference between the value, summing all this value and take the worth of the grand coalition. You take the difference, you can use this as a sort of loss.
Yeah.
Yes, good idea. Good idea, yes. Okay. Please.
Oh, that someone has done this? Oh, really? Okay, cool.
But yes, I imagine, but I don't think with this because it's unpublished. Yeah, yeah, that. Yeah, it's clear. I mean, you must do something like this because otherwise it's uncomputable. Practically, as soon as you have more than, let me say, probably 20 variables, you can do nothing with this. See if you want to compute everything, because you know you get zillion of summons. Okay, the map is the only one. So practically, this guy is for us is the coalitional analog of the Shapley value classical, and although at the end we have this very simple formula, the proofs are based on the Hodge combinatorial decomposition. So we need really to use Laplacian and so on to prove the unicity. It's not based on the formula. Because the formula satisfies the action, but the fact that it's unique is more tricky. Anyway, here we have a little application to linear model. So this is the Shapley that Sayang was asking about before, a way of associating the game to the prediction, let me say. And if you have a very simple linear regression with independent features, so start really with vanilla playing stuff just to understand what happened. Then one can see that the corresponding game is this one by means of this. Then this is, I don't remember the name of that paper. There's a paper from a woman in Norwegia. Okay, she showed this, that SHAP can be computed. It comes out in this way. I will put the proper reference. Making some computation, you practically, in this case, see that our Shapley S, in this case, is a sort of average of the Shapley there, computed in the other way. So in this case, you have this decomposition. In general, it's more complicated. But practically, what our Shapley is doing, if you think a little bit, first, you take all coalition, every coalition, and then you pair S with N minus S. So let me say the opposite coalition. Okay, and you make a Shapley. You give a value to this and the other in the quotient game. Then you take these numbers and you average in an egalitarian way among all coalitions, and you get our Shapley. This is the description, practically, in terms of game theory. So you are Shapling the guys like they are individual, A and B, and then you take the Shapley value, all the Shapley value you find, they form again, and they practically you subdivided the work among all coalitions in an egalitarian way. So it's a mix between egalitarian and marginalist. Okay, so I'm a bit early. I think no one will complain. Okay. Ah, yes.
So instead of having a neural network, right? Let's say my classifier was something like nested trees.
Okay.
Right? Then you should be able to use that structure to very efficiently write out all of those partitions, right? Because each of the computation is something that's nested, right?
Yeah. Yeah, I think so. Interesting.
You have a logarithm algorithm, right?
Yeah.
That's
exactly right.
Yeah. Yeah, interesting. Thanks. Let's go on. Sayang is giving a lot of work to do for me. So at the very, what we want to do now, beside all the things that Sayang kindly suggested, I'm not joking, I'm serious. And first of all, there is another stuff that work on coalition, which is very interesting, which is called Grabish derivative. There is a big book on set theoretic function by Grabish and other, and they work on several indexes. There is an interaction index, there is this derivative, and there is a relation between derivative, Möbius transform, and so on. So this kind of things, okay? And then with application to game theory. And so we have discovered that there is a very neat relation between our differential and at the end our Shapley stuff and the Grabish derivative. The Grabish derivative is that stuff that delta and SUT. I think now you all are acquainted with my notation. I mean, as sets coalition and use again. So if S and T are disjoint, as you see, is a sort of Möbius transformer, but it's not exactly the Möbius transformer. It's very similar. Okay, and this is the definition of the derivative. And now you can see that its derivative has this invertible relation with the differential, and using that we have some formula relating Shapley with his interaction index and other things. So this is one thing we want to develop, and that will come out very quickly, because it's practically finished. So we need more numerical experiment. We didn't have time to do that. I'm sorry, but I would like to present more. We have several already in our repository, several things done by us on standard dataset or our dataset using the classical Shapley. Now we want to use the Shapley, our Shapley, to see what happened. Because as an example, it would be very interesting for us to yeah, okay. It's my timer. It would be very interesting for us. It was almost a motivating example to try as an example, taking the data that we already have on the brain that we use in the paper homological scaffold that we wrote many years ago, and try to see if we are able to cluster somehow the area of the brain with respect to the outcome of the operation. So we want to work on this clustering. And so we think that might be of use as an example in doing pruning, feature selections, aggregating, feature clustering, this kind of operation. You can, no? And last but not least, it can be done something using also C2, triangles, higher relation. That's something I would like to understand as an example. It's not clear to me what's the meaning. Because if I do the order complex out of this poset, simply a triangle is a chain with 3 elements. No? but it's not clear if I add B and the, as an example, you may try to understand what happens if you add B. You go to C passing through B instead going through E, no? As an example. The way is, these things is measuring what happens if you add a group to another group. The other way may be a way of understanding if there is a privileged direction, a better way to do that, let me say, measuring that. This is one thing we want to go on. And then I think I have finished, or not. No, I have already said this thing. Sorry, I'm a disaster. I always anticipate the slide. So, okay, thanks. Then, okay.
Yes, so just because of that seems to be related to, I think it's all relevant variable selection program. So you have an independent variables and variable you want to infer from it. And then there is this problem that you may have a sub-collection of n-1 variables that don't influence the result, but you have another one that people are thinking a lot about it, and that seems to be very related to the problem we are considering here. Is it, or am I maybe?
It's something I have to think about.
Let's try to apply.
Yeah, I don't. I understand what you say, but I don't know. So let me say this: reasoning in terms of like statistical moments. You know, this is like a, you know, it's a single variable. Is an average. What you are talking about is something related morally, something like covariance. And I think that, you know, I think that there you must be a sort of tensor form of the things, because if you want to have a chain of relation, this relation by definition are pairwise. So you need something defined on pair. So you can define on pair, as an example, you can take the game you've done and you take the Shapley of the Shapley. It is stable. It contracts. It remains the same things up to an homotopy. It is multiplied by scaling. It is scaling. Nothing. So once you have done once Shapley, it remains that way basically. So I think maybe mimic something like when you compute variance covariance matrix. So you can, but I'm really brainstorming loudly.
Actually, I'll ask one more question and then we'll do the announcements. Do you think you could use this if I gave you some type of, like, I don't know, disjunctive normal form, and I want to reduce it down, right, in terms of like some logic induction or reduction of the logic? You use this to say that you could strip out all of these coordinates and have the same.
Yes, I don't tell you no, but I don't tell you yes.
Okay.
I tell you, let me think about that. Yeah, I understand what you mean.
Yeah.
You Boolean variable, disjunctive form.
Yeah.
Okay.
I think Pablo has the one. Yeah, so unfortunately, unfortunately we have an additional one deviation in the program. So after the coffee break, we are going through the seminar talks, and Nick is somewhere here. Unfortunately, Jacek Brodsky got COVID and he couldn't make it. I was trying to convince him to join over Zoom, but he is not capable, unfortunately. So we have one talk after the coffee break, and then there will be additional 45 minutes of break before the lunch. And there was a request yesterday to change the order of talks in the later session today. So there's this session with Wanda, Piotr, and Anastasios, and that's exactly the order as it happened. So in the schedule that you have printed, there was Anastasios, Piotr, and Wanda, but now we simply reverse this sequence. So keep that in mind. One of the sessions, the talks are short. That's all. Let's have a coffee break.
I really enjoyed your talk.
Thank you.
Yeah.
Yeah,
I'd be very
I
interested.
appreciate it.
I'd be very interested.
I'm
in
always
using some of this stuff.
I'm always feeling that the things I do are not so interesting. So, but I'm not